series, and in this particular presentation I will be talking about a case study that we carried out to see if using core spatial resolution land cover use maps produced on an annual basis for greenhouse gas accounting could be an option for the UK. Now, why did we go down this route? Well, at the moment for the UK, one of the main sources of information on land cover and use for greenhouse gas accounting is the UK land cover map. This map is mainly based on Landsat TM mapper imagery. And the good thing about this map is that it has 25 meter pixel resolution, and so it provides information about land cover at a relative high space resolution. The big disadvantage is that so far only 3 have been produced in the last 25 years. One is showing land cover for 1990, another one for 2000, and the most recent one is 2007. We're expecting an update soon for the year 2015. Now, for greenhouse gas accounting, we actually need an annual update of land cover and use, and we also need to identify the type and direction of changes between years. We need to know how much one cover type has changed into another. So a product like the global Moses land cover product that is updated on an annual basis is the logical really alternative to UK land cover map. The trouble, of course, with this product, it's only available at 500 meter resolution, and it's produced to deliver good generic global land cover classification. So this map is not necessarily designed to perfectly suit the landscape of the UK. But what if, we follow the example of this global land cover map and we use MODIS data at 500 meter resolution to produce a UK-focused and annually updated land cover? Would a map like that be suitable for greenhouse gas accounting? That was the question we asked ourselves. So would it improve the current situation where we lack the annual update? Basically, the question was, would an increase in update frequency outweigh the loss in the spatial detail that we can get with UK land cover map? So our approach to answering this question was to have a look at the effect image spatial resolution would have on the accuracy of the resulting land cover map. When you think about mapping accuracy, the standard methodology we use in the remote sensing community is, or the other way around, to actually to establish the mapping error, is by using a confusion matrix. Now, this confusion matrix, there's an example here. It's created by comparing the classified map with the reference data. And this reference data is, which we sometimes refer to as ground truth, but actually in reality, it represents a more spatially detailed map or a set of sample points that we believe to be more accurate or reliable. Now, this confusion matrix, which looks like this, gives information about 2 things. The overall accuracy, so there's this number here, and if I get my arrow there, there's a number here, which adds up all the corresponding parts between the reference data and the land cover map. And in this case, you have 72% overall accuracy, and if you turn that upside down, it's a 38% mapping error. What it also gives us is information about the map's performance for the individual classes. And we refer to this as the omission and commission errors. The omission error, along this line here in this particular case, tells you how much the cover class the map failed to identify. So basically, how much of it is missing on the map of that class. And the commission error, it tells us the opposite. It tells you how much of the class shown on the map should have been a different class. So how much of it is wrongly identified as that class. But when you think about confusion matrix, it does not differentiate between the types of error that are contributing to this classification accuracy. So the mapping error that a confusion matrix measures includes error that's caused by the image classification procedure, the space resolution, the image space resolution, that's the bit we're interested in, and also there's other sources of error. There's the mismatch between class definitions of the map and the reference data. Spatial misregistration between the map and reference data, and error in the reference as well. Now we can minimize the mismatch between class definitions by carefully looking at the nomenclatures and trying to match the classes between reference and map. And in our case study, we assumed that the spatial mismatch and the error in the reference data was very small. Now, with the spatial misregistration, that's actually not the case. The error can be quite large. Now, to separate the effect of spatial resolution from the classification procedure, we used something called the Pareto boundary. This method was introduced by to the Riemann sensing community by Boschetti and his team in the publication that I've listed below here and from which this figure comes. You see on this slide. Now, Pareto, what does that do? It calculates the omission and commission errors caused using a spatial resolution that is coarser than the reference data. So, and to calculate it, you use the reference data. And what I mean with that is the reference data that is used to evaluate the classified map, and it is used to produce the confusion matrix. So, okay, so how does it work? I'm going to go really slowly because it's really important you understand this Pareto boundary for the rest of the presentation. So let's have a look at the figures here. So figure A is a starting point. So we start with the reference data. It is converted into a binary map. So, and in this figure, the gray area represents the cover class of interest. Say it's grassland. And the white represents everything else. I'm just trying to get my arrow. There you are. This is what everything else, any other classes. Then we overlay this reference data with a grid that represents the pixel size of the satellite imagery we're planning to use to create our map. And for each grid cell, we produce the percentage cover of the grassland class. And that's that you see that in the figure B. Okay, so you get all the percentage covers for the grass class within the grid cell. Now, to simulate the various solutions our classified map could have produced at the coarser resolution, we now apply thresholds ranging from 0 to 100. So, for example, the solution we would get using a 25% threshold is the binary map of grassland and not grassland, where all the grid cells containing 25% or more grassland cover are classified as grassland in that grid cell and that pixel. So figure C shows this for 4 solutions. The 25% threshold I described, one for 50%, one for 75%, and one for 100%. The next step, which then allows you to produce figure D, and which allows you to create this Pareto boundary. So the next step is to calculate a confusion matrix for each of these solutions by comparing the solutions with the original reference data. And you're producing commission and omission pairs, error pairs. The Pareto boundary in figure D is basically created by plotting these omission-commission pairs for each of the solutions all along the threshold range. Okay? So what this Pareto line represents is the mapping error that's introduced to a particular cover class, grassland, in the example I used, solely by using a coarser grid cell pixel size than the reference data. Okay? So hopefully you've understood what Pareto is doing now. So basically, when you start thinking about this line here, the area on this figure, that represents the B area here, represents the error caused by the spatial resolution of the imagery. Now, if you introduce the omission-commission error for a particular class of the actual classified cover map in this Pareto plot, you can now reveal the proportion of the area that is due to the space resolution, B area. Where's my arrow again? Where's my arrow? Hang on a minute. There you are. And the classification method, which is the A area here. Okay? And these two measures, we're going to, I will mention them in the next part of the presentation quite often in my results, because they're really, really useful to start understanding, to start comparing what's happening in terms of what is the classification, what area is the classification procedure contributing to, and what area is the space resolution contributing to the overall classification accuracy of my map. So let's have a quick look at how this Pareto boundary has been used in the publications by Bossetti and Kutsias in this particular case. So on the left-hand side, this figure shows how you can start simulating different grid cells. So in this particular case, the grid cells of your imagery range from 10 meters, 15 meters, all the way up to a kilometer. And the dots you see here are classification procedures that delivered a land cover map. And these are the omission and commission errors achieved through these classification procedures for a particular class. And you can very quickly see that the range from 10 meters for this particular landscape, from 10 meters to 90 meters, are very similar. The Pareto lines is very similar, the area is very similar. And the moment you shift to 250 meters, 500 meters and a kilometer, that the accuracy is heavily impacted by the pixel size. And another thing you can do is, when you look at the figures on the right, is that you can start looking at different landscape structures. So site 1 and 2 represent different areas, and I think it's an area in Greece or in Italy, it doesn't really matter. And the classification procedures that the dots represent the different classification procedures that were tested, all of them trying to map burnt areas and forested areas in Italy, say. The Pareto boundary shows the impact of the image pixel size that was used, the imagery that was used to do the classification. And basically what it tells you is that the different landscape areas, the Pareto has so basically the pixel size has a different impact on the accuracy, and the classification procedures as well perform differently for the different landscape areas. You can also tell which of the classification procedures are closer to the Pareto boundary. That's what you want. You actually want to minimize that distance from the Pareto boundary to the results from the classification procedure, because that area here tells you that there's scope to improve your classification procedure. Okay? Now, I hope I still have you with me, all of you. And let's have a look now how we implemented and used the Pareto in our case study. So, for the UK, we happen to have two different sets of reference data. We had a stratified random sample of 1 kilometer square areas that we refer to as the Countryside Survey squares, or CS samples, which covers the whole of the UK. We also have data from the Integrated Administration and Control System Survey, or IACS in short, which provides a detailed land use map, a continuous map of the farmland in England. Now, both data sets were not perfect for our purpose. One, the CS one, does not provide a continuous cover of data, but it does provide information on all the landscape components and for the whole of the UK. The other one gives a continuous cover map, but only for the farmland areas in England. So basically, we decided to use both to calculate Pareto and produce confusion matrices. Right. So we use Pareto to look at a couple of things. We use Pareto to look at the impact of space resolution moving from the 25 meter pixel size of the UK land cover map to the 500 meter pixel of a MODIS land cover map. And we were interested to see how it impacted on class area estimates, but also on area change estimates. We had to work with the data that was available to us. So we had the land cover map at 25 meter resolution for 2007, and the CS reference dataset was also available to us for 2007. we had the MODIS land cover map and the Ajax reference dataset, which were both available for every year, and we chose the period for 2006, 2007 and 2008 to work with. And the analysis produced a couple of things. We produced Pareto lines based on the CS reference data. We produced Pareto lines based on the Ajax reference data. And we produced Pareto lines based on the change maps derived from Ajax reference data. And the analysis produced confusion matrices. Confusion matrices comparing the UK land cover map with the CS data and the Ajax data. Confusion matrices were produced comparing the MODIS land cover map with the CS data and with the Ajax data. And then we also produced confusion matrices comparing the change maps derived from the MODIS land cover map with the change map derived from the Ajax data. We translated, before we did all of that, we translated all the data, the land cover map UK, MODIS land cover, and the reference data sets to a common nomenclature, the LULU-CF nomenclature. This was to make sure there was consistency between the data sets and to reduce the mismatch between nomenclatures. We focused the analysis on 3 specific classes, LULU-CF classes: crop, grass, and woodland. What we then also did is to have a look at regional change statistics that we could derive from MODIS land cover with the regional change statistics that we would get from Ajax. And then finally, at the end, we looked at how the greenhouse gas emissions, but specifically just looking at CO2 emissions, were impacted, well, how the CO2 emissions would look when they were estimated from a MODIS land cover product or the Ajax product, and compared the results. Okay, now let's quickly have a look at the results. So the figures here that we see, they show the Pareto lines calculated the countryside survey sample squares for, in here, the 250 meter pixel size on the left, and on the right, the 500 meter pixel size. So the lines you're seeing here represent the Pareto lines for each of the classes that we looked at. So we looked in the green, we looked at woodlands, crops, and grasslands in the yellow. On the right, the colors are the same, but slightly darker. So darker green for woodland, darker blue for crop, and darker orange for grasslands. The dots show the class-specific commission errors found for the UK land cover map on the left and for the MODIS land cover on the right. And what do these figures tell us? They tell us a couple of things. First of all, that the 25 meter pixel is a much better suited size to represent UK landscape patterns than the 500 meter pixel. So that for each of the classes, when you look for the green and the green here, the amount of error that is introduced by just going from 25 meter pixel to 500 meter pixel is quite extraordinary. And it's the same for all classes, but it's a different story for all classes. That's another thing these figures are telling us, is that the impact of the pixel size is class specific. Now, what we're also seeing is that the classification error of the land cover map varies with cover class, and the MODIS performs particularly bad for woodlands. It performs worse than the land cover map, but particularly bad for woodlands. Okay? But also, quickly just by looking at this, the reason why the MODIS map is performing not so good as land cover map, a large part of that is because of the pixel size. Okay, let's have a look at the data in a slightly different way and look at these area measures. Now remember, area B represents the contribution of the spatial resolution to the overall classification error, and area A represents the contribution of the classification procedure to the error. Okay? So when we look at those measures, we can see that in absolute terms, these are this figure and this figure here, both the spatial resolution and the classification procedure so this is the spatial resolution, and this is the classification procedure, have a greater impact on the classification accuracy of the MODIS land cover map. So these are the blue bars here. But when we start looking at the relative contribution of the classification procedure, so basically when we look at the ratio between A and B, which is what we show in this figure here, we see that for the UK land cover map, there's much more scope for improving the classification procedure than for the MODIS map, which I thought was quite interesting. Now, let's have a look to see because all the previous results I've shown is based on the Countryside Survey sample reference data. So let's have a quick look at what happens when we use different reference data sets to calculate the Pareto and the classification accuracy. On the left, I have put all the results together in one plot based on the CS samples, and on the right I've done the same, but based on the Ajax reference data. So the difference is that the CS is a sample-based survey, that it covers the whole of the UK, and the Ajax is a continuous survey, but this one only covers farmlands in England. Generally, we could say that the Pareto lines are very similar, except for the one for the woodland class. And the reason for that is that actually in the Ajax reference data, the woodland areas are very small because the woodland areas that lie within the farmlands are represented by very small parcel sizes. So basically what it's telling us again is that the 500 meter pixel of MODIS is incapable of probably mapping these very small areas, which is actually quite obvious. So yeah, and this is also why, because of the small parcel size of woodland in that area, in the farmland area, this is why the MODIS classification is just the error in the MODIS classification is extremely high. It's basically MODIS just cannot map these woodland areas at all. Okay? What we can also see is that the classification errors of both the MODIS land cover and the UK land cover map are different depending on whether we use the Countryside Survey reference data or the Ajax data. And what that suggests is that the farmland landscape has a different spatial structure to the surrounding area. That's the generic conclusion I can draw from that. Okay, now let's move on to the results related to detecting change. Remember, this particular analysis, the results I've shown you, change detection is only possible using the MODIS land cover data with the Ajax reference data. And what we see here are the Pareto boundaries for the 3 LULUCF classes again, and also for 2 change periods. Change maps generated for the years 2006 and 2007, and these are the darker colors on the map, and change maps generated for the years 2007-2008. So these are the lighter colors these are the lighter colors on the map here. Okay. But the message is very clear now that you hopefully started to understand what the Pareto boundary is telling us, is that the 500 meter pixel is really not suitable for mapping the small parcels of crop, grass and woodland changes that we observe in the UK. And the extreme classification errors are also telling us that the classification procedure is struggling to correctly identify those changes. Okay. So the size of the areas we are looking for in the UK, change areas, are just too small to be mapped at the 500 meter pixel resolution. And this error, of course, is propagated throughout the next bits of analysis we did. So when we derived the regional change estimates based on MODIS, on the x-axis here, and compared them with the regional change estimates based on Ajax, you can see there's quite a scatter of unsystematic errors along the axis where there should be a match. And it's the case for both periods we're looking at. And then when you start looking at greenhouse gas for the case of greenhouse gas accounting, where we don't only need information about the area of change, but we also need information about the direction of change. We're not able to detect, because we're not able to detect the small parcel sizes directly, it impacts, again, on our ability to measure the direction of change. And the figures here compare the results for Ajax and Modi's land cover. And it's very clear that the Modi's-based story of change is totally different from the Ajax-based story of change. And as a result, it will directly feed into wrong CO2 flux estimates. And the main cause of this is because of the coarse pixel resolution of the Modi's data. And because of that, it's very difficult to see a role for Modi's and the UK setup for using Modi's to produce annual derived land cover data that would feed into the inventory work at the moment. So that was a slide that demonstrates that again, where we translated the changes into CO2 flux estimates, and again we are getting different results depending on whether we're using Ajax or Modi's. So basically, the message is not a good idea to use Modi's just because of the pixel size. Okay, so generally the message is it's really important to make sure that the image pixel size that you're aiming for, that you're hoping to use, the imagery that you're hoping to use, has the pixel size that matches the landscape structure you're looking at. And basically, the correct spatial resolution is as important, so aiming for the correct spatial resolution is as important as achieving an annual coverage. And I'm looking forward to hearing your thoughts and questions. And I mustn't forget the acknowledgement. Again, this work was only possible through the funding by the Department for Environment, Food and Rural Affairs, and the support from the Global Research Alliance, and the webinar facility provided by the Global Research Alliance was also helped us give me this presentation today. Okay. Thank you very much.